So this is going to be a little bit of review from your previous math classes, but there are three different types of systems of equations. So the first type that you're probably the most familiar with is what is called a consistent and independent system. So that type of system has some fixed finite number of solutions. Your lines intersect at 1, 2, 3, some distinct number of points. The second type that you can have is consistent and dependent. So a consistent and dependent system has an infinite number of solutions. It's made up of two equations that are really equivalent to one another. They're the same exact line. So any xy pair that's on one of the lines is also on the other line, since they're coinciding, lying like right on top of each other. The last kind that you can have is what's called an inconsistent system, and that means that your two lines are never going to intersect and there is no solution to that type of system of equations.
One method of solving systems of equations using algebra is the substitution method. So it's handiest when one of your equations is easy to solve for a variable. So say that I have this equation in our first example. It would be pretty easy to solve for y in my bottom equation there. So if I go ahead and solve for y, add 2x to both sides, what I'm then going to do is take my result that I got, that y was equal to, and replace y with that value in my first equation. Make sure when you do that you put it in parentheses when you substitute it in, and then simplify and solve, because now there's only a single variable in that resulting equation. So in our case, if we multiply 2 times 4 plus 2x, we get 8x plus 4x, and then I'm going to combine some like terms, subtract 8 from both sides, and divide by 7 to get x equals -1. Now I need my y-coordinate. So if I go back to the equation that I already had solved for y, that's the easiest place to do this in. I'm going to plug my value that I got in for x to get my y-coordinate. So I'm going to have y equals 4 minus 2, or y equals 2. If I was to graph this, you could see that it's consistent and independent. My two lines would intersect at that point. Elimination is another option, and it's especially handy when one of your equations doesn't have a variable that's easy to solve for. So if you look at this set of two equations I've got here, if I was going to solve by elimination instead of substitution, I would want to get my coefficients on one variable to be the same number but opposite signs. That way if I add my two equations together, that variable eliminates and I'm just left with a single variable in my equation. For example, on this one, if I was to multiply both sides of my bottom equation by -2, then I'd have a positive 2x in my first equation and a negative 2x in my second. So if I added those together, my x variables would eliminate because I'd just have 0x and I would only have y left in my remaining equation. So that's kind of the goal for the initial setup here. All right, let's do one. So if you look at this one, I would not really want to do substitution. It's going to be a mess to solve for any of those variables. So I'm going to eliminate y, I think. If I multiply my second equation by 3 and my first equation by -2 on both sides, then I'll have my top equation have a positive 12y and my bottom equation have a negative 12y, which means they'll eliminate. So if I actually go ahead and do my multiplication to get my two new equations that are equivalent but have variables that'll eliminate here, it's going to look like this. Note there are other things I could have multiplied by as well. That just seemed easiest. I could have done the top one by 6 and the bottom one by -4. That would have worked too. So if I add these two that I chose together here, I'm going to have 0y. On my x's there, let me go ahead and get a common denominator. Multiply -8 by 2 over 2 gives me -16 over 2. And then if I add 9 over 2 to that, that's going to give me -7 over 2. Okay, so I've got -7/2, x equals -8. So my y is eliminated like I wanted, and now I could just multiply both sides by -2 over 7 to get my value of x. So x is 16 over 7. And then plugging it back in, you can pick either equation to substitute that x value back into, but I'm just going to go with the first one there. So replacing x with 16 over 7, I will go ahead and multiply and make that 64 over 7. And while I'm at it, getting a common denominator, multiplying 10 by 7 over 7 would give me 70 over 7. Subtract 64 over 7 from both sides, and you're going to get 6 sevenths equals negative 6y. So divide both sides by negative 6, or multiply by negative 1 over 6, and you'll have y equals negative 1/7. So our solution is our 16 sevenths that we got for x, and negative 1/7 that we got for y. Let's take a look at one of our special cases. So if you try some elimination on this one, or substitution, but I'm going elimination, what happens is your second equation, once I multiplied it by 2, is actually the exact same thing as my first equation except opposite sides. So if I add them together, I get the statement 0 equals 0. Now that's actually a true statement, which means that this is a consistent and dependent system of equations where really these two equations are equivalent and all of my points on my lines are shared because they're really the same line. Instead of writing the solution like I have written here, like we did in Algebra 2, I'm going to show you a different way you can write it. So if it is specified in the directions that y is supposed to be our arbitrary variable, what we're going to do is write that coordinate form using only y as our variable instead of two variables x and y. So our solution set's going to be of the form where y is just whatever y happens to be, and then we're going to write our x value in terms of y. So we're going to take one of our equations and we're going to solve it for x, and we're going to put that value in for our x coordinate of this point. So if I take my equation, they're really the same one, so it doesn't matter which one you use, and solve it for x, you're going to get x equals negative 1/2 plus 1/4 y. So my points that will be making up my line are all points of the form negative 1/2 plus 1/4 y, comma, y. So I could pick like any y value, say 1, plug in 1 for y, and you get a point that's on my line. Plug in 2 for y, you get a point that's on my line. Important note, if you had gotten a statement instead of 0 equals 0, a statement that was not true, like 3 equals 4, that would mean this is an inconsistent system and there is no solution.
One thing that you maybe didn't do a ton of in Algebra 1 is solving systems of 3 equations. So it's best to go with elimination. Start by eliminating the same variable from 2 different pairs of equations. So I'm going to take the first 2 equations and eliminate x, which means I'll multiply my second equation by positive 4 in order to do that. So if I jot down what my new equation is going to look like over here, I'll have a negative 4x plus 8y plus 4z equals 44. Be really careful on these. It's easy to make mistakes and I'll screw all of it up, so just be really careful on your rewriting and adding. So if I add those together like I wanted, my x's will eliminate and I'll get 7y plus 6z equals 26. Now stick with the same variable and pick 2 different equations and eliminate x. So I'm going to go with the bottom 2 because it looks like I could put those 2 together, multiply my top one by a positive 3, and then I can eliminate my x's pretty easily. So I'm going to do that. New equation, jot it down here. Again, it's key that you eliminate the same variable from 2 different pairs. Don't eliminate x from one and y from the other. Same variable. So if I add those together, sorry, my work's kind of squished and messy here, you'll end up with 9y minus z equals 77. So we haven't found any values for our variables yet, but I have these 2 new equations that only have y and z in them. So I'm going to put them together, and it's kind of like starting back with a system of 2 equations. I can either do substitution or elimination with these 2 new ones and figure out my values for y or z. I'm going to do elimination because it's my favorite and I just like to stick with it. So I'm going to eliminate z by multiplying my second equation by 6. So you multiply that together. I know that's 54. I'll fix it in 1 second. Didn't realize when I was writing, but I'll go back. So if you multiply those together, you end up with 54y minus 60 equals 462. Okay, I don't need that in between equation at the moment. So if I add those together, I've eliminated my z's, and I can figure out my value for y. So I'll end up with y equals 8. Now going back to just prior to one of my two equations that only had two variables, doesn't matter which, if I plug in my value for y, I can get z. So I plugged in my value of y equals 8, solved this one, and end up with z equals -5. So we're 2/3 of the way there. Now that I have both of those two, go back to any of your original equations. I'm just going to do the top one and plug in both both y and z, and we can solve for x. So it's kind of a long process, but be careful, you'll get there. When we're all said and done, you end up with x equals 0. So solution, make sure you write these in order, x, y, z is 0, 8, -5.